we're now at step 2. And what we're going to do here is that we want to determine the general response. So this term is effectively right out of differential equations, of course. And here's what we know. What we know is that the response is, for any circuit here, it has to be the natural plus the forced response. And what we said about the forced response is that because of our limited time in any circuit semester, I'm going to set that forced response to be a constant. So we always know what that constant is. And where do I get that constant? We get it from step 1. Just like we got it over here, we get it from step 1. We don't mess with that. So we already know half of this. So our whole goal is to get the natural response, which you'll see has a lot more to it now. And my experience is that people typically don't have a problem with the natural response. It's getting the initial conditions. That's what we want to worry about. So what we're going to do here is that we need to go in and sort of write this guy. And what you're going to find here is that when you get this natural response, this now has 2 terms to it. Why? Because it's a second order equation. So that means you're going to get A1 times x1 natural plus A2 x2 natural plus this constant b. So our job now is to go in and start to figure out what are these guys right now. How do I get this complete response? And probably the easiest way that I know how to do this here is that I would have to go in and make an analogy. So what I want to do here is that I really want to do what? I want to interpret these solutions. How do I interpret these solutions? Well, the first thing that I want to do here is that I want to do an analogy. And the analogy that I want to do here is that to understand a 2-storage element like we're talking about, I want to talk about a spring mass system with damping. My experience is that you do not see this in 4A, but you do see this in differential equations a little bit. But what I want to do is I want to go back and I want to start to interpret what this guy does here. A mass spring system is something that was studied a fair amount in 4A. And when I start to look at a mass spring system here, I imagine that I have, actually I wouldn't want to draw it like this, I imagine that I have a spring attached to a cart. And what I do now is that from the equilibrium point, this cart is stretched out. So let's say that you stretch this guy out such that it has an amplitude equal to xm. Where xm is the maximum displacement from the equilibrium. So what happens to the cart? Well, it starts to oscillate back and forth. And if there's no friction, it will do this forever. So what we find here is that if I apply, Newton's second law to the system, what do we get to? So if I now apply Newton's second law, what we see here is that I could write the net force here as what? Just the spring force acting on that object, that this would have to be equal to mass times the acceleration, but the acceleration is the second derivative of position. And if I take this and I manipulate it a little bit, we get something that reads something like this, minus k over mx, and then they define this as minus omega squared times x. So this is the second order differential equation for this system. So now if I look at the solution and what it interprets as, it goes something like this. So now if I look at this thing here, and if I start to interpret what this says here, we get a solution that looks something like this. You'll have a solution where they typically write this as cosine omega t, plus there's this phase constant that you get. So I could set the phase constant equal to 0 for a moment, but what you're really seeing here is that if I plot this guy as a function of time, you're going to get an oscillation that looks something like, you know what, I call this A. I'm sorry, I should not have called that A. I should have called this X of M to keep with this notation. I'm trying to stick to the notation of the book here. So then you'll see that you'll have some oscillation that looks something like this. So how do I interpret that solution? Probably the easy way to interpret this thing and think in terms of its energy. So if I look at the solution here, in terms of the language of energy here, what we see here is that the spring gets stretched. And as the spring gets stretched, all of that energy goes into spring potential energy. So if I look at a point like here, that's where the displacement from the origin is very, the farthest that it's going to be here. And then what ends up happening at some moment like here at the equilibrium point, all of that energy is now converted into kinetic energy. So what this solution says here is that without any damping, energy goes from potential to kinetic energy, and then vice versa forever. That's what that system means here. Well, if I now apply this to an RL circuit, let me see if I could bring this up here real quick. So in a very analogous way here, what we can do here is that we can think about this in a very similar way now. So I can do, if I apply this analogy, so if I apply this to an LC circuit, what you're going to find here is that you can do the exact same thing here, where you have a charged capacitor with an inductor. And I imagine that I've already charged my capacitor here and this inductor, and what starts to happen here is that if I have some initial charge on this capacitor here, what you're going to see here is that we have capacitor energy that's stored between the plates, And when I close this switch, the energy in the form of the electric field is now transferred to the inductor in the form of a magnetic field. And if you remember the equations for energy for capacitors and inductors, a capacitor stores energy as E squared, and the inductor stores it as B squared. So as this thing oscillates back and forth here, you're going to see that the energy stored by the capacitor now gets transferred exactly in the same way as this mass spring system to the energy of an inductor here. Maybe I should write, B and E here. And what I want to show you here is that there's this applet right here. And if I started here, I mean, you can look at what's happening down here, but that's really not important. I'm really looking at how does this E field go from here to here. So right now, what you're seeing here is that I got a fully charged cap. So now I'm going to switch the switch over to here, and you'll see that there's this periodic behavior as it oscillates between those two. So if I start this, the E field is moving. Wow, it's doing it pretty fast here. How about if I reset to slow motion? So this is probably going to be really painful. But we just want to see one cycle, right? So if I started here, the E field has to transfer all to magnetic field. And you can see that the E field lines are getting farther apart, indicating that right there, oh, I can't go back. But you could see that the field was getting weak, and the line density here is getting big, saying that there's a high magnetic field energy stored here, and zero magnetic field here, or electric field here. So then if I resume, then all of the energy from the magnetic field is then now getting transferred back to the electric field. And so, but now you can see that this guy's oppositely charged. So that's half the cycle. So we've only gone to essentially, what, half the cycle. Now it's got to go back. So as it goes back, you can see that I got to go in the opposite direction. Right? It's now. All right, I got it now. And so now you can see it's got to move back to its initial state here. And this is the oscillation right there. So energy-wise, it makes sense, right? Energy-wise, if there's no resistor in the circuit, it's going to do that. So the big difference here is the resistance. What does the damping do to this oscillation? What does the resistance do to this, oscillation? And you're going to find that there are 3 types of damping. And these 3 types here really make a big difference here. So if I continue with the mass spring system, okay, so now if I continue with the mass spring system, but now we add damping. And I'll tell you one thing, this is a huge, huge study in science, these damping things here. And so what you'll find here, that what we end up getting here is that you could imagine that I take my mass spring system and I make it viscous, where I could either put it in a fluid, or there's heat loss in the spring, it's not a perfect spring anymore. Whatever it is here, I could then go in and apply Newton's laws here, where I still have my spring force, but now I add a new term that's related to V, and this term is typically related to the velocity. So this is a speed dependent. Okay, and if you did the modeling project in Physics 4A, you knew that that was studied fairly heavily in that course. And then of course this here has to equal mass times the acceleration, and then you get some scenario like this. So as you do this, it turns out that the solution can be written as follows here. So now if I solve this system, what you can write here is that you could write that the natural response of this system here is then going to look something like this here. You're going to get some maximum amplitude, and then you get one form that looks something like this. Now I chose this form right here. Why? Because you see that you now get some exponential term here. So you get some exponential decay for the dampening. So that's a very normal thing here. And what you're going to find here is that what's really, really important here is the term in the exponential. And what you're going to find here is that the type of response depends on the damping constant. And in this case here, I would label it as B over 2m. So it's this constant that really determines in the exponential term how it behaves here. I just want to let you know that this term doesn't have to be real. It could also be complex. And the complex ones is the one that's painful, because what ends up happening is that you get sines and cosines. And so when I look at this constant here, what you're going to find here is that the response here is that you could get large B over 2m. You could have small over B over 2m. And then you got one that's called critical. So if it's large, this large damping term here, what they call this term here, they call it overdamped. And if it's a small damping, they call it underdamped. And if it's critical, they call it critical damping. And you can go into the lab and you can measure these fairly accurate. And so what it does here is that we can sort of like draw these pretty quickly to get a sense of what they look like here. And underdamping is probably the one that you're most familiar with. And what does it look like? It looks something like this. So they start here and it just oscillates until it goes to 0. And so the green here I would then call underdamping. Now if you look at the overdamped term, the overdamped term with a lot of dampening here sort of does this type of thing. And so this guy would then be called overdamping. And then the critical one is actually can be pretty tricky sometimes to actually get it right. It seems like it is, but it's actually the difference between these two right here. There's a critical value, and that critical value essentially dies off very, 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 very quickly. And how do you know when it's critical? Well, it's faster than this guy, and what you're typically doing with is that as you change the resistance in the circuit, you'll see, the friction in the circuit, you'll find out that it's the one that gets there the fastest and it's typically the difference between these two right here. So you're essentially looking at underdamped with this term here effectively going to zero very, very quickly. And this is critical damping. By the way, door systems are set up to be critically damped. Why? It's the one that goes to zero the fastest. You would think that this overdamped would be the one. It's not. Overdamped just means that it closes very, very, very slowly. It doesn't have to close quickly. But critical damping is what those things are set up for in the door. What's the fastest way to close the door? And they set it, the spring system, to critical damping. So this is, so if I was to say this, this is the fastest to zero. So ultimately, you can see that overdamping looks like it has a big negative constant, but it's definitely not the fastest way here. But I think these are pretty clear when you look at them. So if you look at them with this eye, you'll see that this is exactly what you would be seeing right here. So what we want to do now is we want to start looking at these equations. Okay? So now if I go into an electric circuit, if I do this exact same analogy, it depends on how the resistor is set up in the circuit to get either over, under, or critical damping. And the way we determine it here is that we got to go in and we got to apply the that matrix term that I was talking about. You're going to see that how we get this type, this underdamped, these damping solutions, is we got to go in and we got to solve the matrix now. Okay, so here we go. Let's do that now.